Hello, Chem 1A. This is Chapter 9, Lecture Video 1, and we're going to be talking about periodic table trends. And what periodic table trends are is just a number of properties that actually change based on where the element's location is on the periodic table. So you can see down here, basically, if we compare two elements on the periodic table, we can actually figure out a lot of these properties based on what location that element is on the periodic table. Now, this chapter in your textbook goes into a lot more things than what we're going to cover, so this is all we're covering from chapter 9. And so here's what trends we're going to cover. So we're going to cover effective nuclear charge. We're going to cover that one first because it has a large role in atomic radii. And then after that, we'll cover electron affinity. And these are the three we're covering in this lecture video. In the next lecture video, we'll cover ionization energy, ionic radii, and metallic character. So let's talk about effective nuclear charge. Effective nuclear charge, often symbolized with a Z star or a Z with an asterisk, is effectively, that's a bad word, is the net charge experienced by an electron in an atom that has more than one electron. And this is kind of the net charge experienced while not just taking into the attractive force between the electron and the protons in the nucleus, but also the fact that if you have two electrons near each other, they repel. So it's kind of the net charge after we take into account both the attractive forces and the repulsive forces present in the atom. Now, there's an equation in your textbook on how to calculate this. I don't really need you to know that. I really need you to know the trend, which is that the effective nuclear charge is going to actually increase across a period. In other words, fluorine has a much larger effective nuclear charge than, I don't know, lithium. And this is due to the incomplete screening, is what we say, by the inner electrons. So in other words, the inner electrons, they are only taking a small portion of a +1 attraction from the nucleus because of the repulsive forces that they're also experiencing. And so just kind of showing the Z effective for a bunch of different elements. So lithium has a Z effective nuclear charge of 1.28 for its 2s electron, whereas boron, it almost doubles. It's 2.58, and carbon 3.22, and this is going to keep going up as we go across the row or the period. Now, Z effective or effective nuclear charge, it explains a lot about some stuff that we've been talking about. I just not going to go into it as much. We're going to mainly focus on this for the size of atoms and ions and why it is this way, but it also has an influence on why our orbitals have the energy differences that we talked about in chapter 7, right? S being the lowest energy orbital, F being the highest energy orbital. The effective nuclear charge actually plays a role in that energy differences, in those energy differences. But again, not something I'm going to cover. If you're more interested, you can always read about it. So let's talk about atomic radii. So let's look at the trend. For the most part, the size of your radius of atom, in other words, the size of the atom itself, increases as we go to the left and down, as you can kind of see with those arrows. So in other words, an atom down here is going to be much bigger than an atom up here. Or even an atom right here. This one is bigger because it's further to the left. Or in other words, one here, this one's bigger than that one because it's further down. And you can kind of see that here are a bunch of radii, atomic radii. And all these numbers here are in picometers. So the radius of a fluorine atom, basically that distance there is 71 picometers. right? So, and as you can see, as we go this direction, it gets bigger. Generally, there are definitely some exceptions. You can see oxygen kind of is an exception to the norm, or a couple others. Let's see, I think silicon, no, hold on. Gallium is another exception. Got a little smaller there. And the same thing with germanium. But for the most part, this trend holds, and we're not going to really need to know the exceptions. You just need to kind of know the general rule over here. So let's talk about why we see this trend. So atomic radii increase in size this way due to two things. One, size is going to go up as we go down a group. And the reason for this is because as we go down the group, we have more and more electrons being added to higher energy levels. Higher energy levels are further from the nucleus, which makes the atom much bigger. Now, the other rule is this increasing right to left. Now, that doesn't make sense based on the other one because, atoms over here have more electrons than atoms over there on the left. So why is this the case? And the reason is because of that effective nuclear charge. As we go across a row, our effective nuclear charge increases, which causes the outer electrons to feel a larger positive attraction towards the nucleus and causes them to kind of get pulled in tighter to the nucleus itself. And so that was atomic radii. Let's talk about our next trend, electron affinity. So electron affinity, if you know anything about the word affinity, you know it's kind of, if you have an affinity for something, it's something you like. So electron affinity can kind of be defined as that. It's how much an atom really wants an electron is one way to think about it, but specifically in terms of energy. So when an atom adds an electron, energy generally is released, and you form a negative ion. This has to be in the gaseous state, as according to the definition. So we're going to add an electron to a neutral atom in the gaseous state, and we're going to form the negative ion. In other words, we're going to do this. Cl gas, adding an electron, going to Cl minus gas. And the energy change here is our electron affinity. So in this case, it's a negative value, 349. Now, most electron affinities end up being negative for at least nonmetals. Noble gases don't have any electron affinity values because we're going to find out pretty quick here that noble gases have the perfect number of electrons. They don't want to gain electrons. They don't want to lose electrons. They don't want any of this business, right? So they don't want to gain electrons, so they won't have electron affinities because that's kind of the whole point of electron affinity. This trend becomes more negative as you go up and to the right. So something over here is going to have a much more negative electron affinity than something over there. And you just need to know this trend. Again, if you have any questions about the trends, just let me know. For the most part, the questions you might see are like, put the following in order of increasing negative electron affinity, right? So if we're like Cl, Br, Sr, which one has the largest negative electron affinity? Well, it'd be Cl because it's the highest up and to the right on the periodic table of these three elements. Or put them in order, right? Okay, well then Sr would be first, then Br, and then Cl, as we increase electron affinity going this way in terms of the magnitude, not so much the sign. So questions like that could be for any of these different trends, like how big is it? Cool. Put it in order, or pick which one's the largest out of these three, or four, or five, whatever.